Cool.
So I don't
All
know.
right.
You can feel free to wait for more people to come in if you want to, or just start. I'm not sure if
All
I
right.
don't
I
know how
think
many people are going to come up.
I think Derb said expressed interest. I'll see if I can make it. So, yeah, I'm not entirely sure. I did kind of spring this a little quickly, so I'm not sure who's going to be showing up or not. I'm the only one marked as interested on the event, so
Cool. Feel free to just jump right in.
all right. So I think the story starts when I was looking around YouTube and saw a video on how to induct on the real numbers. And I was kind of curious what that might be, and it got me thinking about different kinds of induction, because classically, induction is built for the natural numbers.
Mhm.
The natural numbers in the standard characterization, the natural numbers are defined by having a zero, having a successor operation, and
Yeah.
the smallest subset of the naturals that has zero and is closed under succession is the whole thing. If you just keep successor operating, you will eventually get to whatever number you pick, and that's the foundation of induction.
Just want to check. You're not sharing anything, are you?
I'm not currently.
Okay. Okay. Sweet.
Maybe I
Yes.
should be. I do have Paint open in another tab in case I want to start diagramming stuff and sharing it.
Cool. Just wanted to make sure we weren't missing something. But yeah, I
Yeah,
agree. That makes sense.
thanks for checking. Maybe I should
Welcome.
move. I did have some notes that I like teched up for like a vague outline of what to go over that I could try moving over here if I can figure out which window I put those in.
Sounds good.
Short expositional thing. Yeah. This desktop. Yeah. It's connected. Yeah. So the set of natural numbers comes with the two properties. There's a distinguished zero element, and there's the successor function. And that is sufficient to get to everything. Now, I did mention that there were a number of side tangents I could go off on, and this is the first one already, which is there is a
Okay.
different. Huh?
No. Just already on a
Yeah.
tangent. 2 minutes in.
Already, yeah. That's how I was planning on this going.
Let's
This is a little
go.
less well structured than the
No worries.
factorization talk was, so I figured I would do this one first when it's a little less time for everybody to prepare. A little less
Cool.
formal here. The
Sounds good.
alternate characterization of the natural numbers, which is that there is a zero object, there
Mhm.
is a successor, and for
Okay.
any other object that has both a zero distinguished element and a successor function, there is a unique function from the naturals that respects both those properties, where the zero is and what the successor operation does.
Sorry, say that again.
So
You, there's a
for
you're providing a different set of axioms for the naturals.
yeah,
Defining them.
different characterization of a natural numbers object. I saw this on like NLab somewhere. Um, but for every object you have that contains a distinguished element and has a quote unquote successor function back into itself, there is a unique function from the naturals to that other object. So you can think of like the distinguished element gets labeled 0.
Mhm.
And then you calculate the successor of that. That has to be labeled 1. Then you calculate the successor of that first object, and it gets labeled 2. You calculate the successor of the second object, and it gets labeled 3. So every natural number is determined to go to one specific place in the other object with the distinguished point and the successor operation.
What is the other
So
object we're talking about? What other object are we
just
considering
any
here?
other object. I might have a vector space with
Okay.
a linear operation into itself and consider like a particular vector to be quote unquote 0, not necessarily the 0 vector, but
Okay.
I would get the 0th one, and then I would get the first one, and I would get the second one, and I would get the third one. So there's a unique function from the naturals that labels how many times I've applied the operation.
I see. Okay. And we
Yeah,
can do that on vectors by just like incrementing the x component or something.
exactly. Yeah.
Okay.
Uh,
That's all.
so so this is that first tangent, which is the category theory definitions that are both weirdly elegant and weirdly opaque. Because if I say the natural numbers object is the initial object with these two properties, that's kind of hard to parse. But it also, yeah, yeah, yeah. Like the, yeah. So it's interesting how there are multiple ways to characterize it. Um, and you might prefer one or the other. You might prefer the one because it's the much more like straightforward to read the definition. I can read the piano axioms and follow um, what's going on. The natural numbers have a 0, they have a successor operation. There's no loops, there's no whatever. 0 is not the successor of anything, it's the first one. And you get induction as a principle. But then it's interesting that same it's also characterized by this like initial object property, which I'll because you just showed up, Derb. I'll say it again because you expressed some interest. Um, the the natural numbers are initial. They have a 0 and they have a successor operation, and they are initial among objects with those two properties. So you label which element is the 0th, and then the 1 has to get sent to a specific number, and 2 has to get sent to a specific element, and 3 has to get sent to the successor of that, and 4 has to get sent to the successor of that. So for any other object that has a distinguished element and a function into itself, you get a unique function from the naturals into that element or into that object that respects those properties. That was a. I hope that made sense. It was a little fast. All right. So that was the first tangent. Is the naturals are like built for induction according to the Peano axioms, but there are also other characterizations where it's an emergent property, and we can show that we can demonstrate induction from the initial object property, because if you had a subset of the naturals, this might be where I want to share screen, um, paint. Can you guys see this?
Yep.
Yep. All right. That is not what I wanted to do. Where's the? Yeah, if I have the naturals and I have a subset of the naturals, probably should. Oh, do they?
Oh, cool.
Whiteboard. Oh yeah,
I didn't know
there's
about
one. Whiteboard. Join or launch in DM. Join, probably. Did you make one?
I see it. I think
You
I'm
see
writing
a
on it.
whiteboard, right?
Yeah,
You were
I'm
writing
writing on
on
the
a
whiteboard.
okay, cancel. Where's the whiteboard?
It should like show up sort of in the list of participants.
Okay. Okay. Drives. All right. Um. Oh, it is. It's still sharing. Thought I thought I canceled the share screen.
I still see it.
Oh, you were tying to them. Okay.
Wait. Oh, I see. Huh.
Okay. Very cool. All right. So yeah, where was I? Right. If we have a subset of the natural numbers, which I've gone through 3 letters, I'm just gonna. I figure M is probably all right. That's not taken by anything else.
Taken by the it's taken by the natural
Okay.
numbers.
Natural numbers. Oh no. It's a good thing we're not talking about those today. Those are secret. You got to know. You got to get more degrees to talk about the natural numbers. We're
Okay, what
gatekeeping it real hard. Okay.
what are we looking at here? What is M?
Okay. So you can use the initiality property of the natural numbers to prove that they have induction. So if I suppose that I had a subset M of the naturals and that it had 0 and that it was closed under the successor operation,
Mhm.
then it has to be all of M. And the reason is if M has its own successor operation and it has its own 0 element, then I get a unique function from N back to M.
That makes sense.
And because M has a 0 and M has a successor operation, and that's what N does, is it gets a unique function into anything with those 2 properties. And if I follow the arrows up there and then back, then this is a function from N to itself that respects the 0 and
Mhm.
respects the successor operation. But there can
Right.
only be one such function, which means this has to be the identity. And that means that the image of this containment here has to be all of N. If this function wasn't surjective, the inclusion of M into N, if there was anything in N that was missing, then this couldn't be the identity function.
That tracks.
So initiality of N means 2 things. It means that N has no extra elements It's the smallest thing that has the zero and the successor and is closed under the successor. And it also doesn't have any extra relations. If I go from point A to point B to point C, this can't loop back to point A because there are
Right.
other objects that n would need to have functions into where that doesn't happen. So the initiality property does characterize the natural numbers, and it does prove that they have induction. But if you phrase it in this way, as opposed to the Peano axioms way, induction is a theorem about the natural numbers and not an inherent, not a defining property of them.
Mhm.
So we might wonder what other kinds of induction there might be. If I go over here, do you see anything? No, I'm not sharing screen, right? I'm just glancing at my notes. I'm just glancing at my notes, like I'm not showing the windows, right?
I don't see anything.
Okay. All right. Yeah, somebody mentioned order type omega. I forgot who that was, or maybe wasn't paying attention. Also, how do I erase things?
I think.
Here's extra colors. Oh, thank you, whoever that was.
Yep.
So, if induction is a property of the natural numbers, but it's not the defining property of the natural numbers, we might wonder what other kinds of objects have induction. And somebody mentioned order type. So the natural numbers are sort of the most basic kind of objects that would have be infinite and have like an inductive principle, but we also have, they kind of look like this. I got the first one and I got the second one, and I can keep going. But if I'm talking about ordered sets, I might as well consider the natural numbers union infinity.
Mhm.
There's a stronger form of induction, which says if I have any, if instead of assuming that it's true for the previous number, I go from point A to point A plus 1, with quote unquote strong induction, you might need to assume more pieces. So if I know that it's true for like every number beneath 4, and then I can use that to prove that it's true for 4, that's also induction, but it's called strong induction because it's equivalent, but it feels stronger.
Does it feel stronger?
But yeah, but it also like generalizes better. So it
What does
like
it
feels
generalize
strong
to?
because you have to assume that it's true for every previous number instead of just assuming that it's true for the one previous number.
Mhm.
Yeah,
Right.
yeah, that's what. Yeah. So
What is it? So, what is an example of what this generalizes to that you can't do with normal induction?
well, you can do it with normal induction. It's just maybe like a little cleaner if I phrase it this way, which is if I suppose it's true for every number less than n, then it's
Mhm.
also true for n.
Sure.
And the reason this generalizes well is if I assume that it's true for every natural number less than this infinite point I've added, then it's true there as well. So I can use the same principle throughout the whole object instead of adding a special case at infinity.
I see. Because if you
So
were using normal induction, there is no previous element. So yeah, yeah, that makes sense.
yeah. And there's another one I could use, which might be more convenient at certain times, which is the infinity is a limit point. So if I pick a sequence approaching infinity, and I assume
Mhm.
it's true for every element of that sequence, then I can prove it's true for infinity. But like, we can either consider limit points special and use a stronger assumption just for them, or we can kind of uniformize it. It's just what's convenient.
That makes sense.
Well, if I'm adding one infinite point, I may as well add a second one. If I call this
Sweet.
omega, I might as well call this omega plus 2. And I can also induct on this object. Or I could induct on this object. Or I can keep adding more points. What's to stop me from adding an infinite number of them?
Is this what is meant by
And
transfinite induction? Or is that
transfinite
when
induction. So you get transfinite induction up to various ordinals. Tools? Where is the erase button? I should learn where that is.
you can select the area just by clicking and dragging, and then press delete.
Well, if I click drag,
exit the pencil mode.
yeah, I'm looking for where that is. I'm not sure.
It's like the default operation.
Okay.
Like if you just have the toolbox
go.
where it says like GIF and the pencil and the shapes.
There we go. Yeah. I was in the sub window for the pencil, and it wasn't obvious how to get out of it.
Ooh.
Okay. Thank you. Yeah. So I can do induction at omega, and that's just the natural numbers. I can do induction on omega dot 2, where I just stack two copies of the natural numbers on top of each other. Equivalently, this would be like the naturals times the set 0 and 1.
Mm-hmm.
Reverse that. 0, 1 times the natural numbers with lexicographic ordering. So,
Right. 0, 0, 0, 1, 0, 2, 0, blah 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 up to 1, 0.
Yeah. Well, I could add a third copy of the naturals by extending this.
Mm-hmm.
Or I could just keep adding copies of the naturals, and I could get n squared with lexicographic ordering. And that's also an ordered set, and I can also perform induction on it. Induction is still a theorem that I can derive, this transfinite induction. Okay, did my audio cut out there? It said reconnecting, but that might have just been the whiteboard app.
I think you're good.
Okay. So transfinite induction I can do up to n squared. I can do up to n cubed, where I take 3 copies of n and multiply them together and use lexicographic ordering. And if I just keep going, if I take n to the power of n, except I can't quite do that. I have to take the sequences of natural numbers, is what this would mean, where almost all elements are 0.
Why do you need that caveat?
Because it's not a countable set otherwise.
Are you saying you have to have an infinite number of, or rather, you have to have a finite number of non-zero entries? Is that the idea? So that you can. Okay, so that there is.
I'm trying to get to omega to the omega and not up to something much higher yet.
Okay.
I'm trying to stay in countable ordinal land for a bit. So the like finite sequences, so to speak, that eventually hit 0 and stay there, have this order type. And if I use other more clever constructions, I can get even higher order types. We can make sense of this. We can even make sense of this, if we just like add some diagonal ellipses, we keep taking omega to the power of itself over and over again. That also gets us a sensible ordinal, and we can use the sequence style induction all the way up to like this point.
I mean, as long as you have a well ordered,
Yes.
this still works, right?
Yeah. This actually is a limit of something. It's not where the sequence induction style stops working, where I say, I get the successor operation on these, and I get the limit of a sequence operation at these points, the limit points.
Mhm.
But this is where Peano arithmetic starts to break down. So I can give explicit examples, like the finite sequences of natural numbers, gives me omega to the omega, or I can give you an explicit example of omega to the omega to the omega. But every ordinal less than epsilon naught, you can provide a construction in Peano arithmetic for an exotic ordering of the naturals that has that order type. For instance,
Why is that?
What?
That's not obvious to me. I'm curious to know why.
Okay, so these are all countable sets,
Uh-huh.
which means they're all in bijection with n,
Yep.
which means that there is an exotic way of ordering n. And the question is, can I construct an explicit ordering of n that that gives me this order type? And to give an
Wait.
example of this
Maybe I'm
one,
misunderstanding what you mean by like order type. The order type of n itself is omega. Is that correct?
yeah, with the standard less than equal sign, we get omega.
But by means of a bijection, you can just biject it with some other set that has a more fancy order type, and for that reason, we just call
Yeah,
it a reordering of n to yield that
yeah,
fancier order type.
I can pull that weird ordering back onto n somehow
Okay.
and
Yeah.
say, I'm going to talk about fancy less than equals. This gets me a new order type. So for this one, for example, omega to the omega,
Mhm.
I can look at two numbers and I can say x is less than y if, when I write out their prime factorizations, the power of 2 is less, or they are the same and the power of 3 is less, or they are the same and the power of 5 is less, or it's the same up to that point and the power of 7 is less. And I can keep going, and that gets me this kind of finite sequence thing, because my sequence that eventually ends is what the exponents are in the prime factorization. Eventually, it's all 0.
Mhm.
And I'm
Yeah.
comparing these
Yeah. That makes sense.
sequences lexicographically. Yeah, so there's an
Right.
explicit ordering of n, and I can prove that it's a well ordering.
Okay. Yeah. I
For
follow.
all ordinals below epsilon naught, Peano arithmetic can prove that can provide specific examples of orderings on n that give those order types and prove that they are well founded.
What does it mean to be well founded?
So well founded, I think, means just that it's a well ordering, and maybe I feel like I should double check this just to be sure. Um, okay.
Okay. So
Yes, thank you. So it does relate back to the purpose of the talk. I was hesitating to say that. Thank you. Um, yeah. Okay. Thanks. That's the so it's like half of the well order condition.
Well-founded. Wait, say that again. A well-founded total order is a well order. So you're saying if an order that is, what did we say? That an order that is decreasing and has a finite amount of elements, and it's total.
So
Total meaning contains all elements.
the
Sorry,
yeah,
what was the
so
condition then?
the well order condition is um sorry, no, what's the well-founded condition works for partially ordered sets. It means if I keep going down, eventually I have to stop somewhere, like the natural numbers. If I choose to start at 7, I can go at most like 7, 8 steps before I have to stop.
Wait.
Um,
The wealth. Hmm, sorry.
eh, yeah, if I choose a sequence that decreases strictly, then it can only have finite length. That's it, right? I have to start somewhere, and then I have to go down from there. So even at omega dot two, you know, I would want to start if I was trying to make it last a long time, somewhere in the second half, right? Okay.
Well-founded. Well-founded. Sorry, what was the okay? What was the definition of well-founded? Is that the one that is you have a finite decreasing sequence that has a minimum, or like you can't. What is it? There's a minimal decreasing sequence. Okay.
Yeah.
Okay.
So for assuming choice, then in omega dot two, for example, I could start my sequence here, and then I have to go down. And I can only go down finitely many times before I hit this.
Mhm.
Then I have to jump some finite point in the first copy of it, and I have to keep going down.
Okay. Yeah.
And if I was doing a partial order, I might have extra things off to the side that aren't comparable. But my
Yep.
my sequence that's going down has to eventually stop or hit 0.
Mhm.
So up to some kind of choice, I guess the well-foundedness condition is this: if we go down, we have to hit a bottom at some point. Um,
Okay. Yep. Makes sense.
so you can construct an ordering of n with this order type in Peano arithmetic, but you can't use Peano arithmetic to prove that it's well-founded. And this is the smallest ordinal that breaks Peano arithmetic in this way. Um,
So
stronger
so you
systems. Yeah.
I was gonna say what so you're saying yeah, you're saying there's some axiomatic system that is more strong than piano arithmetic, and it does prove that epsilon
And
naught
it
is
does prove, yeah, it does
okay.
prove the well ordering of an an order on n that looks like this. Yeah.
Okay. Cool.
In fact, you can use this concept to measure the strength of a proof system. Um, you look at the smallest ordinal that the theory can't like demonstrate well-foundedness of in some sense. Um, and Peano arithmetic gets quote unquote strength epsilon naught because this is the first ordinal that breaks its ability to provide specific orderings on n and prove that they are well orderings. This was one of the tangents also was
Cool.
proof theoretic ordinals. It's kind of interesting.
The
I'm not the expert on those, but
you don't
yeah.
have happen to know the proof of
Happen
why
to know
that's
the
the
proof.
case?
The proof I think is by Gensen. that if you wanted to look it up. But I don't know the proof off the top of my head. It's probably not short.
Okay.
Yeah.
I
Yeah.
see.
It's not gonna be like not gonna be like the classification of finite simple groups, but it's not like easy, I think. Yeah, I haven't read the proof.
Gotcha.
Um, hmm, interesting.
Hmm.
Thank you.
Cool.
Yeah, I'm done talking about this. You guys done with this part?
Yeah, I guess so.
All right. So, up to that point, the sequence definition still works, where um, I use a successor operation for all these parts, and then I have a sequence that approaches this limit point, and that's how I get induction up to there. And then I have more successor ordinals, and then I have another limit ordinal, and I use the sequence thing to get up to there. But this does eventually also break because we have this ordinal, which is uncountable, the first uncountable ordinal. And that approach can't work for induction up to this point because there is no sequence of countable ordinals approaching this one. If there was a sequence of countable ordinals approaching this one, then this would be the union of countably many countable sets, which would contradict that it's uncountable. So if we want to get induction up to omega 1, we have to move from sequences up to taking the like suprema of sets, for instance. So I have to move to that strictly stronger sort of induction where I say everything less than this point is true, then I conclude for the next one. That works for both limit points and the successors. Maybe I don't have to do that. Maybe there's some complicated way of phrasing it, but that's where the previous strategy breaks down. And we can keep going. You can make very, very large ordinals, and you can talk about transfinite induction up to those ordinals. I think, like ZFC proves that transfinite induction is valid up to every like well-founded, up to every proper ordinal, because that would be part of the definition of ordinals. They're well ordered. Yeah, transfinite induction is valid as a theorem. I got to be careful of saying things because I'm not the expert in that area, and there are occasionally things that you can phrase very slightly wrong. Like for instance, Piano arithmetic can give you an example of an ordering on n with this order type. It just can't prove that that's corresponds to an ordinal. Right. What was my next point? Yeah, each countable ordinal are also uncountable ordinals that come with their own transfinite induction. We have to move to the strong inductive step at that point. We can also induct on sets that aren't well ordered. So the video I mentioned at the beginning that kind of kicked me off thinking about induction on different sets was the title was something about induction on the reals. And I don't remember if I watched the video or not. I probably did at some point. But one way to induct on the reals, I guess first I should talk about what induction means. For purposes of this discussion, at least, we'll say that induction needs a base case of some sort and some sort of inductive steps. So the base case might be it's true at 0, or it's true at some number. And the inductive steps might be it's closed under the successor operation, or it's closed under taking suprema and the successor operation. This might be it's closed under taking the suprema of subsets. This might be it's closed under taking the suprema of sequences. You can come up with like different kinds of induction by mixing and matching different sorts of base cases, different kinds of inductive steps that you can do. There's probably a text tool that would make it easier to type out. Yeah, there is. So for induction on the real numbers, we might, for instance, take our base case as we can go arbitrarily low. Wait, hang on. I just realized there was a thing I forgot to write down here, which was the conclusion. Which is if S satisfies the base case and is closed under the inductive steps, then it has to be the whole set we're working with. Let's call it T. All right, that was a little scatterbrained, but if I lost anybody?
No.
We're good? Okay. So for the reals, T equals R. We might choose the base case to be I can go arbitrarily low. And the successor step to be if I have an element of S, I can get a bigger element of S. And if I have any two elements of S, I can take the whole closed interval between them. It's closed under convex combinations. And the first one that I can choose a bigger element, saying that it doesn't have a strict maximum. You can also phrase that as being closed under something. What was it? Yeah. If X is in S, then there exists some. Well, I guess my notes didn't say that you can phrase that as being closed under something, but they did say you can phrase that more like a step, which is if X is in S, then I can find a bigger one. What was the original way I wrote that? Yeah, that has no X in it. All right. But if I assert that I can find arbitrarily low elements, and I assert that I can always find a bigger element, and I assert that it's closed under convex combinations, and I assert that it's closed under taking suprema, then I can sort of say, if I want to prove at a specific number, intuitively I'll like keep going until I'm beneath that number.
Yeah.
And then keep going until I'm up above it. And if I ever run out of room, then I will take a limit and then keep going again until I'm above it. And then I'll take a convex combination between this point and this point.
Okay.
That's the intuitive story for how the induction works. But because R is so big, that actually can't be your proof. Because you might, if I was choosing this, if I was choosing these things, give you a lower element and give you a higher element adversarially, I could choose them to be
you could construct them so that you just converge to some point that's like really close by.
Yeah. And we have a way around that in our inductive thing. If I make it converge somewhere, then you have to also have that point, and then you can make me start taking steps again. And then we can
Right.
take that point, and you can make me start taking steps again. And I can slow down how far these are getting. Well,
Right.
now this is another set, and you can take the
Yeah.
supreme of that, and but I can keep playing this game up to any ordinal you want.
Right.
I can make my things arbitrarily adversarial and stop you from inducting to the number you want to get to.
Mhm.
So this is where it kind of gets to like constructive math. This is what the difference is. Because if you want to prove it in a positive way, which is how we like think about it intuitively, if I want to prove it in a positive way where I can actually reach a number beneath, I can actually reach a number up above, and then I can use the convex combinations to get to exactly the number that I want, then I can thwart that plan by just picking a really, really, really bad function for you to give you the next, to satisfy these requirements. But at the
Mhm.
same time, if I allow for negation, proof by contradiction, let's assume that this was not the case. Let's assume there was some unreachable number. Then you have to have something beneath it. You have to have some set that's reachable. It has to stop at a certain point, but R is complete, so I can hit that point. That must not have been the top. I have contradiction. So uh, constructive proofs are interesting because they are, in a sense, strictly stronger. Because I can actually tell you, here's an algorithm for proving at the number that you want using these tools a finite number of times, or something like that.
Right.
Um, this is still a theorem, but it can't be proven constructively because there might be this extremely adversarial choice of steps. I thought that was kind of interesting. And that
That is kind
segues
of
into the
interesting.
next thing. I think I wanted to talk about this for a bit longer. What was that?
That is interesting. Is there like,
Yeah.
I guess first of all, is there a name for this technique? Also, what's like a problem that you
Uh,
would actually want to use this on? Like where you have those exactly those operators.
where you have exactly those operators. I'm
Like,
not
is this
really
just
sure.
a kind of a contrived like tactic, or is there some like real example of a problem where you like have exactly these tools at your behest, such as like finding the supremum and like being able to jump back some amount?
I don't know. You can think about how there might be a problem like that.
Yeah,
I don't
it
know the
doesn't seem completely unimaginable, but I can't think of one off the top of my head.
yeah. Application isn't really my area, so
Yeah.
Mhm. Oh yeah.
Mhm.
Yeah.
Right.
You might say, in a sense, this is what it is for art to be complete in a very like non-constructive way, because it's all about reaching these like top points, and no matter what ordinal we pick to be adversarial, you can't do that. You can't find something finely grained enough to like escape the structure of R.
You could do
Um,
this on the rationals too, though, right? It would be a similar idea.
you you can do things on the rational, but the problem is like, uh, suppose that I was looking at the numbers strictly between negative root two and root two,
Mhm.
and then the problem is we don't have those as limit points, so we don't get
Right.
the
Right.
supreme
Yeah, that's true.
closure. You have to phrase it in a different way. Yeah,
Yeah.
and this does kind of segue into what I was going to talk about. Um, so inducting on more complicated sets tends to involve additional or more complicated inductive steps or even base cases. So when we were doing ordinals, up to finite numbers, we don't even need infinitely many steps. If I want to do induction through all of n in one go, I have to have a sort of global statement about n as my like inductive principle. If I want to go up to higher ordinals, I need to start considering limit points. If I want to go to uncountable ordinals, I have to throw away handling limit points with sequences, which I don't know how many people do that, but it was an option up to uncountable ordinals. And then it isn't past that point. And when we go to R, we have to even make our base case really complicated. It has to be, I have to be able to find arbitrarily low numbers or something that's interchangeable with that somehow. And I have to make my inductive steps complicated. Be able to take being closed under convex combinations is really strong. I just have to get below it and above it. It gives me everything in between. I don't have to do any sort of iterative process to home in. And
And we're
we
juxtaposing that
choose.
with you said the naturals, like then general ordinals,
Yeah.
then uncountable sets, and then the reals. The difference between uncountable sets and the reals being like the lack of a minimum element. Is that why
Well,
we're
there's
drawing the
that.
line
I think
there?
I can kind of
Yeah.
embed them into the reels. I think I'm actually not sure how. I'm not actually sure how large of ordinals you can embed. You surely you can. Okay,
Wait,
can you
why
not
not?
even embed omega one into the reals? Okay, I believe that.
Why not? Wait, I don't believe that. Why not? I don't follow.
I believe.
Mhm.
Um, sequence of real numbers that approaches that.
Oh, right.
That's
Oh,
clever. I like that. Yeah, but all of those contain omega one. All the other uncountables do, right? So wouldn't an embedding of those also embed omega n just as a subset? Okay. Yeah. I think that it's true though that all uncountable ordinals can't be approached by a sequence of, well, we could say a sequence of smaller ordinals because omega one plus one, I can just start at omega one, right? Yeah, if I take omega one plus omega, then I can approach this with a sequence of strictly smaller ordinals because I can just start at omega one and then just have my sequence be in this part, right? How much I add on top of it. Yeah. But I can't embed the whole thing at once into R because that would embed this as a subset, and this is wacky. All right, thank you. That is good. Good discussion. I'm liking this. Where was I though? Right. Yeah. As we're making our sets more complicated, it seems like our inductive steps and even base cases have to get more complicated to handle the extra structure. So I was thinking of what's the strongest sort of inductive principle that I can come up with that uses like the weakest assumptions. And because so many things are going to be equivalent, what I mean by the strongest sort of inductive principle is how constructively strong is it? Like, if I assume my principle, I want to be able to prove that this works with R, because it should give me the tools that I need to apply this however much infinitely many times I need, that even a super adversarial thing couldn't get past me. I want it to be an induction principle that works on R and kind of out of the box, which means it can't be constructively provable. This is what the Brouwerian counterexamples. I'm not sure if I'm pronouncing that right, but there are a lot of theorems of classical mathematics that can't be proven constructively. So there's this interesting technique of if I have thing that I want to prove, if I can show that it implies one of these true statements that's not constructively provable, then this also can't be constructively provable if this part was constructive, the arrow.
Mhm.
So it's not a contradiction because it's not like a false, or at least it's not a falsifiable statement. Maybe there's a model of the constructive thing that doesn't obey classical rules, so it is actually false in that model. But there are other models of classical math where it does hold, assuming consistency with ZFC or whatever we're working in. Which, if that's not consistent, we have other problems as a field of math. I think isn't consistency of ZFC isn't ZFC like equiconsistent with like IZF or something? Um,
I don't know either.
what is IZF?
What is IZF?
Intuitionistic Zermelo-Frankel. It's some attempt to do set theory constructively, at least more constructively. I don't really know anything more about it. So that's it. I think I was talking to a friend who told me about this once, and then I think I tried to look for a reference later and couldn't find one. Um, but I'll update you if I get back to him and get something interesting. There are a lot of interesting constructive systems, and there are a lot of interesting consistency proofs or consistency like quote unquote proofs, like simply typed lambda calculus. Lambda calculus doesn't give you a consistent theory because you can form terms that reduce to themselves. But if you add types onto lambda calculus, you can make it consistent, and you can prove consistency by showing every formula that you can write down has to reduce to like a unique normal form. There's no like non-terminating computations. Okay, yeah, that's I think it's that. So it's a computational system on its own, but you can associate simply typed lambda calculus to a type theory. And I think consistency for a type theory means there are no you can't construct an element of the initial object. So like the object that corresponds to the truth value false false implies everything else. There's a function out of this empty type into whatever type you want. The function out of the empty type is, you give me an element and I'll tell you where to send it. That's the function. Like yeah. So the if I go to the type-based definition of consistency, I think I can model this with a non-terminating computation somehow. I don't remember exactly what the details are, but if I take that back into lambda calculus, then what consistency means in the type world translates to, in lambda calculus, the condition that there shouldn't be non-terminating computations, which there are, I think. Like you have a notion of consistency in lambda in type theory, and if you translate that condition in type theory language backwards into lambda calculus, I should stop talking because I don't actually know for sure, but I remember that it has to do with the bottom type. No, that's all right. I went way off track talking about type theories. It's actually surprisingly easy to make these inconsistent. If you have time, look up system U. You get like simply typed lambda calculus is really simple. You have some very basic operations and type things, but you don't get like dependent types. There isn't a way to say, here's a natural number n, give me a type of the vectors of length n. There's not a way to take terms into types, and there's not a way to make types that depend on terms. There's not a way to make terms that depend on types, and I don't think there's a way to make like type trans. I forget what the third one is in the lambda cube, but if you can make a whole cube by adding additional things to lambda calculus, and they all can be proven to terminate in the same way all computations have to terminate that are written in these systems. But when you try adding a third level to this hierarchy with types terms, if you try adding kinds and doing some very basic things with that, it becomes inconsistent, I believe. That's system U. I might not be remembering that perfectly, but it's interesting. That is more of a tangent than I was intending to go on, which is saying something.
So just to, even if we've missed the
Yes.
exact details here, the point is that if you can somehow use induction on that system, that is, what are we contradicting? That if we embed
Well,
some kind of induction scheme inside of like the lambda calculus, what's the
so
point?
what's the point? The lambda calculus thing was separate from the entire point of the induction thing,
Oh,
I
okay.
think.
Okay. I thought we were gonna
Yeah.
like put induction into
Yeah.
like reductions on
No,
like rewriting systems or something.
no, it must have been related to like proof strength or something. Oh, the constructive mathematics. Right.
Oh yeah,
It was related
right.
to constructive mathematics and
Yeah,
the strength
intuitionism.
of
Yeah,
different constructive systems. Yeah.
right.
Um, right. But my goal at this point was to find an inductive thing that was very strong constructively. I can't.
Mhm.
Yeah, when adding it to a constructive system as an axiom, it um, immediately implies this kind of real induction. It immediately implies all transfinite induction, um, which you can't do directly because if I choose my thing adversarially, you might not ever get where you want to go. And sure, if you take limits enough times, but your proof would have to be infinite in length to cover all the horrible. If I give you any, if I give you any particular functions to use for this, I can always find something small enough, and I can always go larger. I've forgotten. I've boxed these so many times. If I give you specific functions, you can probably write down a proof that those are sufficient to do induction. But the point is, I could choose worse functions, and I could always choose worse functions. I could always choose worse functions, and you can't give me one proof that works for all of them simultaneously. It's kind of like how with piano arithmetic, like I can get, without using induction as an axiom schema, I can prove that if it holds at 1 and it holds with successors, then I can prove it up to 5 just by writing down 5 steps of my proof. Prove it for 0, prove it for 1, 2, 3, 4 using the inductive step. But without induction, I can't prove it for all of n simultaneously.
Right.
If you give me any finite stopping point, I can prove it up to there. But to get the whole thing all at once, that would be an infinitely long proof. And in the same way, to handle all the awful functions I might throw at you, this kind of induction, you would need an infinitely long proof for. If you were doing it constructively. That doesn't work. Oh, no, I have not seen the chat. Where can I open the chat while I'm presenting on the whiteboard? Ah. My mic is starting to buzz. Does it sound all right currently, or?
Yeah, it's buzzy.
Okay.
I can still understand you, but it is a bit buzzy.
Let me try. Can you hear me better? Oh, it might be my computer's fan or something. Am I still buzzing?
You are still buzzing. I don't think it's the fan.
Okay.
I'm guessing it is like something digital happening. Although
Something digital happened.
it's fine. Yeah, yeah.
Just in case, I'm going to like elevate this to and hope that does something. We'll see. My computer had like a structural issue, like the corner of it got bonked, and there's some stuff wobbling around in there. So for all I know, something might just physically be on the.
It sounds like digitally getting messed with, like. Yeah. Yeah.
That's the case. And if I move this wider out of the way.
Whoa, wait. I think that actually fixed it. Wait, say something now.
Well, that's amazing. It was the charge cord wire was going underneath the computer, and I just moved it to the side. I had no idea that would do anything. You learned something new. All right, I'm back. I'm glad that fixed it.
Yeah, you're good.
So
I wonder if we could like, presumably it's an AC cable. I wonder if we could like, by listening to you, compute the frequency of the AC charger.
yeah, probably. I'd like to buy a new cable for this because this charges through USB-C, and it has the. I'd like to have that port available.
Yep.
It has like one of those circular charge pin slots. It's just the charger I got with the computer goes into the USB-C port. Anyway.
Okay, sorry for derailing.
That's all right. It improved the mic quality, so we're good. It was productive.
We had fun along the way.
We had fun. Yes. The real mathematics is the friends we made along the way. Um,
Okay, so I'm dying to know.
usually
Did you solve this problem? Did you
yes.
figure out the way to do real induction?
I did come up with an inductive principle that I liked. Perhaps I'll erase all these things now. We'll leave the word base there. Why not?
Maybe I'm missing the like. Why how am I cheating by just saying like have an induction schema where you can, if you have an arbitrarily low element that you already know to begin with, um like you can just make like some epsilon neighborhood for like an epsilon that is known beforehand, like that would work. Like I feel like the induction schema that you pick has to depend on the problem that you're trying to solve in the first place. So like,
Yeah.
I mean, I could
So
just come up with some kind of like contrived induction schema where like,
there are
I
a
just,
lot of options. There are
yeah.
options that are valid. My challenge to myself was to try to pick one that felt as weak as possible, or felt like as strong, makes the weakest assumptions, right? So I don't
Okay.
want to have the quote unquote user of the theorem prove that it holds in a little epsilon ball. I don't want to
Okay.
have the user prove that it
Okay.
holds
Yeah.
for like arbitrarily low quantities.
Sure.
I want to give them I want to require as little as possible.
Okay. Yep.
So,
That makes sense.
in search of that, I let the base case be it's true somewhere.
Okay.
Now, if it's just true somewhere, then I'm going to need a way to go down as well as up. So, let's say if I have an element A in S, there has to be able to there has to be a has to be a way to find a smaller element than A, and there has to be a way to find a bigger element than A. These are the first two functions I'm going to require.
Okay.
I can go down and I can go up.
Mhm.
Except I want to include as many sets as possible in here. So I'm not going to say there has to be a way to go up because I might be working with a set that ends. So I'm going to state either there is nothing above A in my set T that I'm working with ambiently. I've scrolled out a little bit. Can everybody see the letter T there? Okay. Um,
Sorry, why are we talking about an ambient set all of a sudden? Like, what is the ambient like?
okay.
This is
So
an ambient subset of the reals.
I'm going to do induction, and because I want it to be as strong as possible, I'm going to pick a set T. And I'm going to try and work in that context and make few assumptions about what T is,
Okay,
as I can get away with.
copy.
So T might be the reals. T might be omega 1. T might be some other ordered set. I'm just going to assume that it's ordered for now, and we will have to come back to that later. But if that's all I want to assume, then T might have a maximum. So I have to say there has to be, either the set of things in T above A is empty, or it includes an element of S. So I guess going back to what induction means, quote unquote, I'm going to have a set
Mhm.
S, I'm going to make some assumptions about it, and I'm going to prove from those that it's equal to T.
Okay. Yep.
And that S equals T conclusion from my assumptions is going to be the inductive principle that ideally is going to be very strong constructively.
Okay.
So
Hello?
thinking intuitively is fine here because if it's not constructively possible, that's perfect. That means we've found like a Browerian counterexample. It's a stronger inductive statement. So I can go up and I can go down unless I have hit the bottom. But now here's a problem, which is if I give you this kind of stepping, how will we reach this element that's in between? So I'm actually going to replace this with the rule S is a subset of T. Put that back up there. I'm actually going to replace this with the rule. The base case is going to be, let me write this down. Not the pencil, the inductive steps. If A and B are in S, can you see as I'm typing, or do I have to click off it before?
Yeah, we can see.
Okay. If A and B are
Wait.
in S, then
Should our base
each.
case be that there are two elements of S for the inductive claim to function?
No, I'm just going to let you choose A equals B if you want to.
Oh, okay, sweet. A comma B in each of. Ooh.
So T is some totally ordered set. It's the only assumption I've made about it so far. I'm going to need to make more assumptions. And I'm going to need to have some sort of completeness. So intuitively, this gets me pretty far. This is all I want to be doing most of the time. But if I was an adversary against these operations as they are, I might choose my lowering to converge somewhere that isn't at the bottom of T. And I might choose my uppering to converge somewhere. Or I might choose my middleman sort of thing to converge away from the point that you actually want to get to. So I didn't think of a way to get around the necessity of having this S is topologically closed in T in the order topology. That's maybe the biggest assumption. That's one of the biggest assumptions we're going to have to make about S.
Wait,
And
sorry, we're constructing S, but is this a? What is this statement? Is this this is an assumption or what? Because
yeah, so these are the requirements. You know, in like constructive math, there's a close correspondence with computer programs, right?
Mhm.
So if I go with that analogy, I am trying to decide what I need from the user of my proof to give them the result that
Okay,
they
I
want.
see. I see.
Yeah,
This is an assumption for your inductive principle to function.
yeah. I need
Okay.
you to provide me with qualities of S, and I will give you
Okay.
just a
Yeah.
magical oracle that says S equals T.
Okay.
So you need to give me an element of S. You need to be able to give me this function. You need to be able to give me topological closure of S in T, which is maybe a lot to ask. Then again, maybe the other inductive step is as well.
But like the user who invokes your oracle doesn't know what S is. Like the user is just like, are we asking them to
Yeah.
show that like every subset of S is closed in T, or?
So if we go to like how induction is like classically stated for n, it's like the natural number has some property, right?
Mhm.
Um, every natural number, let's say, has a prime factorization, ignoring zero. Every natural number has a unique prime factorization.
Oh.
Well, if we go with that, we can change perspective into asking about the set of natural numbers that have prime factorizations that are unique. That's what's playing the role of S here. I've got some quality I want to prove, which is going to be all elements of T are in S.
Mhm.
Is how I'm going to phrase it.
So the user has to provide the fact that for some S that could have possibly been constructed using these mechanisms, it would necessarily
Yeah.
be topologically closed, regardless of what the specific algorithmic, where we are in the algorithm in having induced things into S. Is that what you're saying?
Yes. So
I
you
may be
can
getting that wrong. I'm not sure.
you can think of S as something like the set of elements of T that obey a nice rule, like natural numbers having prime factorizations.
Mhm.
So you're going to use whatever quality you want to use to pick the S that you want. You're going to pick the S that you want, and it needs to be able to satisfy these conditions. Then I will tell you S equals T.
Okay.
So now the problem here is that think about the rational numbers, which you brought up earlier. It's a great point. Because the set of numbers between negative root 2 and positive root 2 that are rational is non-empty. We can always pick lower, higher, and further in between elements of it. And we have topological closure in Q under ordering. Because if this is my negative root 2 to positive root 2, then this union of open sets is the complement of that. Because these 2
Mhm.
points are missing.
Right.
So this is the point at which we will need to assume something about T. We want to make it as weak of an assumption as possible. And I think this is where I spent the most time, was trying to decide what kind of completeness would be right to ask for T, because I want this to work for R. I want this to work for, asking that it works for R and then relating it to constructive math is maybe a little weird, because the constructive real numbers are a strange beast. Just as something to say in case, for people who might not be familiar, there are only countably many real numbers that you can construct, because there are only countably many
Relatively many
constructions you can give.
constructions. Yep.
Yeah. So the real numbers are very, very strong in their supremum property, and using all the tools of classical mathematics. If you want to do them constructively, you end up with a set that might feel a lot more sparse,
Mhm.
and that makes certain theorems. It makes a lot of things very weird in constructive analysis. For example, equality of real numbers under the standard. A real number is a number I can approximate arbitrarily well. If you give me like a size of interval, I can give you a lower bound and an upper bound within that interval that contain the number, something like this. And these like things have to nest in a certain way. Right? If I pick that to be my definition of what it means to be a real number, equality is not decidable. I can give you different representations of the number 0 that can't be like proven to be different.
Mhm.
You'll
Yep.
never find a proof, or maybe it's that I'm remembering a fact and I'm trying to justify it. from beforehand, not knowing for sure what the proof was. But maybe it's that if you give me any attempt at a proof technique, I can give you an adversarial couple of constructive real numbers that are just too close to tell apart. Something like that. But the point is, like, you can't always tell them apart. And as a consequence of this, the only constructive functions you can make on the real numbers are continuous. Because if you had a discontinuity, again, going back to the Browerian counterexamples, you would be able to use this to detect, is a number greater than 0? Applying a shifted version of this function. So constructive real numbers are very weird. The only functions you can make are continuous. There are only countably many of them that you can actually reach. This is related, I think, to weird facts about model theory, where systems that have uncountable objects have to have countable models, where from an external point of view, the constructive real numbers are countable, but from an internal point of view, you still can't enumerate them because the approach you would have to take to enumerate them would exceed the capacity of your system to, prove that this is a valid and complete numbering. Like Gödel gets involved and things get weird. Stop talking because I'm not the expert and I might accidentally say wrong things. But hopefully that makes sense. I haven't been interrupted in a while, so I'm not entirely sure how well that explanation went.
I got I think I got the vibe. I don't know if I could recite or prove any of that, but
okay. Constructive real stuff is weird.
Yep.
So,
I'm with you there.
So it's maybe a bit of a reach to be talking about constructive mathematics and saying that I want this inductive theorem to work on R. Because which version of R do you mean? They're very different.
Right.
But I'm going to need to assume some sort of completeness property, which you might not be able to give for like standard constructive real numbers or something. I haven't actually gone through and checked. But the kind of thing that we want to rule out is this infinite sequence approaching a point. So our first attempt might be to say that our completeness is going to be like sequential completeness. But that is simultaneously a lot to ask and not sufficient. The reason it's not sufficient is our old friend omega 1. Because if I take this ordered set, does it zoom out on your screens when I zoom out on mine? Also, how do I drag?
It does not. Yeah.
Okay. Right click to drag. Thank you. Okay, I'm going down a bit. Just for space. Omega 1 plus star plus omega 1. Sorry. What this means is that I'm going to take this uncountable ordinal and I'm going to take it flipped upside down and I'm going to put something between them. In the same way that I would stack omega on top of omega, and just say, all these ones in the right one are greater than the ones in the left one. We're just kind of taking a union of sets. I'm going to make this construction. And we have sequential completeness here. Maybe I didn't want this star here in this example. Sorry, I remember doing that for something, but Can this be dragged? Yes, it can. Okay. Omega 1 and omega 1 star. I have sequential completeness here. There is a gap. I can, in a sense, like approach from the left side and approach from the right side. This is like a separated set. This is open as a subset, and this is open as a subset. So that is the topologically weird ordered sets that I was talking about in the yeah, omega 1. I have sequential completeness because you can't give me a sequence that approaches the gap. There, there is a gap, but the uncountableness of omega 1 um, and just the weird bigness of it at the upper end breaks my ability to approach. Now, this is a problem for us because under our assumptions, we would not be able to induct from the lower half of this construction up to the upper half. We might be able to get, using classical mathematics, power up to this breakpoint, but we can't go past it. So, and at the same time, sequential completeness is a lot to ask. So, what I came up with instead, which isn't perfect, but does feel like the best I could do, was inspired by the like nested closed intervals completeness property. If I have the normal version is if I have a sequence of nested closed intervals, then the intersection of them can't be empty. And this is a characterization of like the completeness of R, and the fact that the rational numbers are not complete because I can make upper and lower bounds on root 2 and squeeze down to in the limit 0 size and not have anything in the intersection that's rational. Is everybody scrolled to a point where they can see the three levels of those brackets?
Yeah.
Okay. I just want to make sure that I'm not like traveling outside your view and leaving you all behind.
You're good.
Sequences won't work, but what I can demand. So we've flipped again. I want a powerful kind of induction, so I'm going to require as little as possible. But now I'm handing this back over to the user. I want to make something that is easy for the user to do. So I want the user to be able to require as much as they want. So I'm going to put a lot of conditions on this before I say there has to be something in the intersection. And what I came up with was this has to be a well-ordered collection of a well-ordered set of nested closed intervals that it has to be. Which direction does the order go? So this is the direction of greater. Smaller intervals are considered higher up. Because the next interval goes farther in. Yeah, it's like reverse inclusion or something. So yeah, I just want smaller intervals to be higher up on the list. I'm going to, you can make like a space of nested closed intervals ordered by reverse inclusion. That's a partially ordered set. And I'm going to demand that you give me an ordinal and that this collection of sets that you give me has to be an embedding of that ordinal into the partially ordered set of closed intervals ordered under reverse inclusion, which is a lot to say. But this was one of the strongest thing I could come up with was if the user is handed a a set of nested closed intervals that has all of these properties, it's got like well ordering, and if I take like a limit of a bunch of these nested closed intervals, the result has to be another nested closed interval. That's the completeness property. You know, if I go up to a level that is represented by a limit ordinal, then that has to be the intersection of all the levels before it. You know, this is a lot for the user to be asking of the mysterious entity that is challenging completeness of T. Does that make sense, or have I lost anybody? I feel like that was
Uh, I,
complicated.
I get the requirement.
You get the requirement.
Yeah.
Okay. So that was requirement number 1 on this sequence of.
That's a good
So
question.
so there's at this point there's myself. I'm trying to give the user a very permissive inductive principle. And there's the user who can be as poorly behaved as they want, giving me these weird sets T that might not be complete. And we've moved on to a mysterious third entity trying to challenge to the user their claim that this T is complete. You know, it might be me again, right? If I want to give you this inductive principle, you need to show me that T is complete. So the user, given that I'm trying to give them as much like privilege as possible, has to be able to ask a lot of me if I'm going to try to make the claim that T isn't complete. I have to give them a counterexample, and the counterexample has to be nested closed intervals of this form. So the user doesn't necessarily know what they're going to get, but they're going to know a lot about whatever they do get because I'm going to have to provide all of those proofs to witness to them that my counterexample really does break the inductive principle for their set T. Does that make sense? Not really. Okay. Um, okay. I offer. Okay. Tell me if this does the trick. I offer induction. In order to do this, I require base case inductive steps, um, completeness of T. This means something that we've talked about, the base case. The inductive steps we've also talked about. We're trying to just use topological completeness and the fact that we can go like up, down, and in between. And this third one is the completeness of T. You have, in order to show me completeness of T, I want to require as little of you as possible. You have to be able to withstand a challenge claiming that T is not complete. Wow, that moved in the least helpful spot possible. Uh, under, no. Um, there we go. Visible again? Okay. I have to be able to withstand a challenge claiming that T is not complete. And I want it to be easy to withstand this challenge because the user is the one who's withstanding the challenge. I want to make things easy for them. So you get to know a lot. So as many
Yeah, yeah. I'm starting to. Yeah, I'm starting to
okay.
lose the plot on who's what's.
Okay. Yes. Yes. I offer induction S equals T. Users set S equals T. This is going to be my theorem. I'm giving them induction as a classical theorem that is definitely, definitely, definitely not constructively true. In order to prove this theorem classically, I want to require as little of them as possible so that it would be constructively easy for them to give these things to me. So the user, so it's going to be a theorem of classical mathematics and not a theorem of constructive mathematics. So that's what I need something for. I need it to be classically true. So I need to make some assumptions. So I'm going to require them to give me the base case. I'm going to require them to give me the inductive steps. I'm going to require them to tell me that T is complete. But I need this to be a weak condition as well. Base case, I just need one element to exist in S. Inductive steps, I just need to be able to go up and down. I need topological closure of S. And that's as little as I can get away with asking for. With completeness of T, I want this to again be as little as I can get away with asking for. And because I'm thinking about them having to construct things, the user, I want to give them as easy of a time as possible. So a challenge has to be really easy to defeat. If a challenge has to be really easy to defeat, I'm going to do that by making the challenger, perhaps me, give them as many things as possible. So, to challenge completeness of T, you need to show that there is a gap. And what it means to be a gap is you need this well ordered set of nested closed intervals. Does that make sense? That doesn't converge to anything. Yeah. Okay. Okay, so the intersection being a closed interval comes from I want this to be yeah, I want to require as much as possible, and I can't get away with a sequence of nested closed intervals because omega 1's too big. So this has to be indexed by an ordinal anyway that might be of arbitrary size. Because if it wasn't of arbitrarily big size, they could come up with a bigger set that's like omega 1 and use this same construction to create a gap that's too hard to detect. Right? Um, so it has to be ordinal indexed set of nested closed intervals. And if I'm requiring a lot from it, I'm going to require that this ordinal indexed set of nested closed intervals is like agrees with the ordering on omega according to reverse or agrees with the ordering of the ordinal according to reverse inclusion. And I'm going to demand that it be like a continuous like an embedding of that ordinal into the set of all the closed intervals, the partially ordered set of all the closed intervals. So that's where this intersection has to be a closed interval comes from. I'm not going all the way to the end of that. Yes. If I'm okay at so the ordinal that I'm indexing with, um, I don't demand that the intersection of everything be a closed interval right now. What I'm demanding here is that the limit ordinals contained within this ordinal, at index omega, it has to be an intersection of intervals 0, 1, 2, 3, 4, 5, 6, and so on. The sequence that approaches omega, if I take the intersection of all of that, has to give me the one at index omega. And the sequence that the intersection of all the intervals up to 2 omega or omega 2 has to equal what is indexed as omega 2. And yeah, yeah. But I'm not demanding anything at the endpoint right now. Um, actually, I will demand something at the endpoint, which is just because I can throw on an additional condition here. To make this challenge as hard as possible, we're going to require this whole ordinal indexed set of nested closed intervals and the intersection of all of them must contain at most one element. So if you are going to claim to have a gap, then I want you to get exactly in on the gap. You have to find this space. There can't be anything extraneous in there. This whole intersection has to contain exactly the one element or nothing. And the completeness property I require is that if we zoom in on this, there has to be exactly one element in there. If I give you this whole collection of intervals that seem that close to find a gap, and I give you the additional property that there is at most one thing in there, then you can say, here is the one thing. Yeah. So I can yeah, I can now write down like the full inductive principle. So I'm going to try to go down to the bottom of the page, I guess. or at least a little farther beneath this beneath these intervals. Typing. I'll give everybody a minute to find the typing. Got it? All right. Given T that is totally ordered, complete in that I'm not sure what the shortest way is to type this, but the condition is that if I have that ordinal indexed as a continuous embedding of the ordinal into closed intervals ordered under reverse inclusion, and the intersection contains at most one element, so you've really honed in on a gap, then there has to be exactly one element in there. So if I try and find you a gap, you can find me something that fills the gap. And the reason I would want to do it this way is because, like, thinking back to constructive real numbers, with the completeness property there is you try and find a gap, and that is what it means to have a real number, is you have something that looks like it's trying to close in on something. Then there's a real number there. All right. Non-empty for this is my claim. If I am given a set T that is totally ordered and complete in that very strict sense that if you try and close in on a gap, and you really are closing in the sense that you're not capturing any more than one thing, then there has to specifically be one thing in there. And given that complete set, which would include the natural numbers, it would include all these ordinals, it would include R, it would include if we have omega 1 and put one thing above it, and then put omega 1 upside down above that, that would be included. Any sort of countable set, uncountable set you might hope to do induction on with ordering. This is the best I could come up with that includes as many of those as possible. Now, given a subset that is not empty, you can go up and you can go down, and it's topologically closed, then S equals T. And this is the titular weird induction that I came up with.
So is there you have proof for this?
I do have a proof.
I can vaguely see how the ingredients mix together here, but I certainly don't have a vision of the whole thing.
So the trick is sort of by construction, but this is not going to be something that's constructive. So the proof that I came up with uses proof by contradiction like 3 times. So
How long of a proof is this?
it's like a page of LaTeX or something. I don't remember, but
Okay.
I can give the gist pretty quickly.
Sweet.
So we give an element of T that we want to hone in on.
Okay.
We want to hone in on this, and we start over here using non-emptiness.
Okay.
And then we're allowed to go up. But if we chose adversarially, this might be really bad and it might never get us there. So instead, we'll use proof by contradiction, which is suppose that I could not get high enough to get above this point.
Yep.
If that was the case, then I have a like supremum somewhere, supremum in the. I can use this property of closing in on a gap to try and find something because I have all the
value
tools.
that you're trying to hone in on.
What?
Yeah. No, sorry. Continue. Yeah, I follow.
Yeah. So because I have all the tools of classical mathematics when making this proof, I can take this weird closed interval thing and use it to actually find a supremum of all the things that are in S.
Okay.
And my claim is that it doesn't reach that point. But using this condition, there actually has to be something at this supremum, and then I have to be able to go yet higher. Contradicting it was the supremum. So proof by contradiction number 1 done. We can get as high as we need to. Proof by contradiction number 2, basically the same thing. We can get beneath it. Regardless of where this started, we can get above it and we can get beneath it. And then proof by contradiction number 3 was look at the set of elements that are like less than this and what's the supremum of those, and I have to have something exactly there. The elements that are greater than this point, I have to have something exactly at the infimum. And so if I tried to choose like a smallest element that's greater and a largest element that's smaller, then I can use this third AB to find something strictly in between those, which contradicts this part. So I have to be able to get above the point I'm interested in. I have to be able to get below the point I'm interested in. And once I have an interval containing it, I have to be able to get smaller intervals until I'm exactly at the point. So my original point under consideration had to be in S. And because it was arbitrary, S equals T. Maybe it wasn't a page and a half of LaTeX. It feels like that would be pretty short if I combined things together.
Yeah, I think that makes sense.
Yeah. But that is also an illustration of how strong proof by contradiction is. No matter what I was doing to try and get higher, an adversary could always choose the worst possible step up function, step down function, and step in function, and make it impossible for my proof to account for it. But proof by contradiction by itself takes all of that and makes the proof easy.
Right.
So this here is an inductive condition that I could give to a constructive user, like a gift from heaven that solves all these problems, that is actually like pretty easy as a theorem of classical math. So now the question would be like, how strong is this? And I don't know. What I do know is that it immediately implies all sorts of transfinite induction, which you can't do constructively, so that seems pretty strong. At least I'm pretty sure you can't do that constructively. So that seems pretty strong. But I am not sure if it is all the way as strong as something is equal to its double negation. As proving proof by contradiction, excluding the middle. I'm not sure whether this is sufficient to exclude the middle or not. What? I think there are at least some that are as strong as excluding the middle that you wouldn't expect necessarily. There's something about choice. Like you can try to add some variations of choice into constructive mathematics, and some of them are weaker than lem, and some of them are imply lem, I believe, just by themselves. I think the full axiom of choice implies the law of excluded middle, even in a constructive framework. Don't like quote me on that before you look it up, but but that's the example that comes to mind. Yeah. So that's it. This is the neat little project that I did that took me on a bunch of tangents, and it did take a while to come up with this condition. For a while, I was trying to prove that it worked with just sequences of nested closed intervals, and then somebody gave this omega 1 gap demonstration. Oh, thank you, Axiomatic System. That looks like an interesting paper. I will open that up to read later. Cantor-Bernstein implies excluded middle is the name of the paper because the chat isn't recorded.
Actually, it is.
Oh, actually, it is.
Yeah.
Oh, good.
This time it is, at least.
Okay. Yeah, I have not had the chance to go back and look at the previous recordings.
Speaking of which, Jared, are you going to post yours? I'm looking forward to it. Oh, you're going to edit it. Is it going to be pretty? Yeah, I'll stop anyway.
Forward to seeing the combinatorial